welcome to WikiPodcast. Imagine a universe where the very act of trying to pinpoint one aspect of reality makes another inherently blurry. It's not because our tools aren't good enough, right? But because that's just how reality works at its most fundamental level. Today, we're taking a deep dive into one of the most, mind-bending and foundational concepts in modern physics, the uncertainty principle. This is a really crucial idea in quantum mechanics, and it's all about the inherent limits of measurement. So let's unpack this. What exactly is the uncertainty principle? Because, for many of us, it sounds pretty counterintuitive. We think of precise measurements.
It absolutely does, yeah, because it really challenges our everyday intuition, doesn't it? At its core, the uncertainty principle, famously associated with Heisenberg, states that there's a built-in kind of unshakable limit, a limit to how precisely you can simultaneously know certain pairs of physical properties of a particle.
Okay, certain pairs.
Yes. The most famous example is position and momentum. Think of it like this. The more accurately you try to pin down a particle's exact location, the less accurately you can possibly know its momentum. That's its mass times its velocity at that very same moment.
Ah, okay.
And, vice versa. If you know the momentum precisely, the position gets fuzzy.
And this is where it gets really interesting for me. Because my first thought, and probably, a lot of listeners' first thought, is, oh, okay, we just need better instruments then. So this isn't about our technology being clumsy or simply disturbing what we're trying to measure. It's not like if we build some quantum supermicroscope, we could just beat it.
You've hit on the absolute crucial distinction right there. No, it's absolutely not a limitation of our technology. And it's not merely an observer effect where our measurement physically disturbs the system, though actually that was an early thought people had. This principle is an intrinsic property. It belongs to quantum systems themselves.
Intrinsic. Wow.
Yeah, it arises directly from the wave-like nature of all quantum objects. Everything, electrons, protons, they behave not just as particles, but also as matter waves. It's a concept first proposed by Louis Broglie.
Okay, so a wave. Here's where it gets really interesting for me again. How does this wave nature cause such a fundamental limit? I can picture a ball, sure, but a matter wave that has a fuzzy position and momentum. Help me visualize that.
Okay, let's try an analogy. Maybe think about a musical note. If you want to know the exact moment a note is played, its precise position in time, it has to be a very short, sort of sudden burst of sound, right?
Like a clap.
Exactly. But a short burst like that doesn't give you enough time, enough cycles of the wave to precisely determine its exact frequency or pitch, which is kind of like its momentum in this analogy. The sound is too smeared out in terms of frequency.
Okay, that makes sense.
Conversely, if you want to know a note's frequency with absolute precision, it has to ring out for a long time, like a pure, sustained tone.
A hum.
Right. But then you lose all precision about when exactly it started and ended. Its position in time becomes fuzzy. It's really the same idea for a quantum particle. If you want to know its position with high precision, its matter wave needs to be highly localized, like a very tightly squeezed wave packet.
Squeezed wave.
Yeah, but to form such a tight wave packet, mathematically, you actually have to add together many, many different waves, each with a different momentum. So this makes the particle's momentum inherently uncertain or kind of smeared out.
Ah, because it's made of many momentums.
Precisely.
Yeah.
And if you want to know its momentum very precisely, meaning the particle's wave is a pure single wave, like that long sustained musical note, then its position becomes extremely spread out and uncertain. Essentially, it could be almost anywhere. This fundamental trade-off, it's deeply rooted in the mathematics that describe waves. There's something called the Fourier transform, which relates how spread out a wave is in space to how spread out its constituent frequencies or momentums are. It's a mathematical fact that just shows up in physics.
So this isn't just a vague fuzziness then. There's a way to actually quantify this limit, isn't there? Like a hard boundary the universe sets.
Absolutely. It's not just philosophical. We quantify this precision, or rather the lack of it, using standard deviation. You often see it symbolized by sigma, the Greek letter. The uncertainty principle sets a fundamental lower limit on the product of the uncertainties for these pairs of properties.
A lower limit, okay.
Yeah, for position, let's call it uncertainty, sux. And for momentum, sups, this hard limit is known as Canard's bound. It says a sux times sup is always greater than or equal to a specific number. That number is Planck's constant divided by 4. Physicists usually write it as IO2, where Alice uses the reduced Planck constant.
Planck's constant. That name keeps coming up in quantum mechanics.
It's the fundamental constant of quantum mechanics. It's incredibly tiny, but it dictates this fundamental limit. It tells us just how fuzzy things have to be at minimum.
Can we see this in action? I mean, beyond these theoretical examples or analogies?
Definitely. Consider a really simple system, like a particle confined to a tiny box in quantum mechanics. It's a standard textbook example. Even in this super constrained system, if you calculate the product of its position and momentum uncertainties, it always exceeds that fundamental limit, too. There's just no way around it, even for something trapped.
Yeah.
Or think about something called coherent states. These are found in systems like a quantum harmonic oscillator, which, okay, sounds technical, but they're incredibly important for understanding things like lasers. These special stats actually manage to achieve the absolute minimum uncertainty allowed by the principle. They hit that A2 limit exactly.
So they're as certain as possible.
Exactly. They represent the most classical-like quantum states possible, but they still obey this fundamental cosmic rule. It's truly inherent, baked into the fabric of reality. And, if we connect this to the bigger picture, there's another critically important pair of properties subject to this principle: energy and time.
Ah, yes, energy-time uncertainty.
Right.
The energy-time uncertainty relation, usually written join, is greater than or equal to 2, links the precision of a system's energy to the time duration, join, over which it exists or is measured.
So does that mean if a particle only exists for a fleeting moment, its energy, and I guess by Imasikari, its mass can't be perfectly defined, how does that manifest in the real world, maybe in the subatomic realm?
That's precisely it. A really well-known application is with unstable quantum states. Think of excited atoms or certain subatomic particles. They only exist for an extremely short time before decaying. Because their lifetime, or join, is so short, their energy isn't perfectly definite. It has an inherent spread. We often call it a natural line width.
A line width, like on a graph?
Yeah, if you were to plot the probability of measuring different energies for that state, it wouldn't be a single sharp line, but a broader peak. It's like trying to sing a musical note very quickly. If you only sing it for a split second, it's hard for someone listening to tell its precise pitch.
Right. But if you hold the note for a long time, its pitch becomes very clear. It's the same idea. The faster a quantum state decays, the shorter its lifetime at, and the broader its energy line width vaguely. This is why, for example, in particle physics, the mass equivalent to energy of unstable, fast-decaying particles. Take something like a delta particle, which might only exist for maybe 10 or 8 seconds. Incredibly short.
Wow, that's fast.
Extremely fast. Its mass energy has a significant inherent variation because of that short lifetime. For instance, a delta particle's mass energy can vary by about 120 MeV-C.
MeV-C energy units for mass.
Yeah, it's just C in action.
Right.
Physicists often quote mass and energy units divided by c squared, mega electron volts per c squared. The point is that 120 isn't a measurement error from our detectors.
It's real.
It's an intrinsic property of the particle's existence, stemming directly from its fleeting nature via the energy-time uncertainty principle.
That's fascinating. But, okay, this raises a question I think many listeners might have. If time is involved in this uncertainty relation, why isn't time treated quite like position and momentum in quantum mechanics? I've heard it's not an observable in the same way, all right?
That's a really profound observation, and honestly, it's one of the trickiest and most debated aspects of quantum mechanics. You're right. Unlike position and momentum, which we think of as properties of a particle that we can, in principle, measure directly with an operator, time, well, time is generally not associated with a single particle operator in the same standard way.
So it's different.
It's often viewed more as an external parameter,
Right.
kind of like the stage upon which quantum events unfold, rather than an internal property of the quantum system itself that you measure. This distinction makes its formal mathematical treatment much more complex and sometimes even controversial. How to properly handle time in quantum theory is still a subject of deep thought. It fundamentally changes how we think about time in the quantum realm compared to our everyday experience.
Okay, so stepping back a bit, where did all this begin? Who first started wrestling with this, inherent fuzziness idea?
Well, the man himself, Werner Heisenberg, he first conceptualized this back in 1926. He realized that the mathematical structure of quantum mechanics itself, specifically something called non-commutativity, implied this fundamental uncertainty.
Non-commutativity, like multiplication where order matters.
Exactly like that. In quantum mechanics, measuring position then momentum gives a different result, statistically, than measuring momentum then position. The math showed him that this difference wasn't zero. and it implied you couldn't know both perfectly. His famous 1927 paper formally introduced the idea, and to illustrate it, he proposed a simple but really powerful thought experiment, the Heisenberg microscope.
Right, the microscope. Tell us about that. What did it reveal?
Okay, imagine trying to pinpoint an electron's position and momentum simultaneously using a theoretical microscope. You have to see it, so you shine a light, a photon, on it. Now, if you use a short wavelength, high-energy photon, you need short wavelengths for good resolution to see the position precisely.
Like a gamma ray microscope.
Sort of, yeah. That high-energy photon gives the electron a large, unpredictable kick. It changes its momentum in a way you can't fully control. It's like trying to find a billiard ball's position by hitting it with another billiard ball. You find it, but you've also changed its motion drastically.
Okay.
Conversely, if you use a long wavelength, low-energy photon to try and minimize the disturbance to its momentum, well, then the position measurement becomes vague because the long wavelength gives poor resolution. You can't pinpoint it accurately.
Because you're stuck.
Exactly. Heisenberg showed that no matter the photon's properties, you couldn't precisely know both position and momentum simultaneously. There was always this trade-off.
And for a while, people thought that was the uncertainty principle, that it was purely about the disturbance from the act of measurement. But you made a really important point earlier that it's actually more fundamental than just a disturbance. How did our understanding evolve from that initial disturbance idea?
That's a critical point, yes. Niels Bohr, who was Heisenberg's colleague and mentor and another giant of quantum theory, he later refined Heisenberg's explanation. Bohr argued very persuasively that the principle wasn't simply about an unavoidable measurement disturbance. It was actually rooted much deeper in the inherent wave nature of quantum reality itself, like we talked about with the matter waves.
Back to the waves.
Back to the waves. This crucial distinction led to our modern understanding. It's not just that we can't measure both precisely, it's that in the quantum realm, both properties don't even have perfectly defined, simultaneous values to be measured in the first place. The fuzziness is real, it's intrinsic. Later on, other physicists like Hanard, Robertson, and even Schrödinger provided the more rigorous mathematical formulations that we use today, really solidifying this understanding of its intrinsic nature.
Wow. This whole idea must have really ruffled some feathers back then, especially among scientists who believed in a perfectly deterministic universe, where everything could, in principle, be known if you just had enough information. Sounds like a direct challenge.
Oh, it certainly did, a massive challenge. The uncertainty principle, along with the broader Copenhagen interpretation of quantum mechanics, which Bohr championed, became central to these incredibly intense debates that really shaped 20th century physics. The most famous, of course, was the long-running intellectual duel between Albert Einstein and Niels Bohr.
Einstein versus Bohr, the clash of titans.
Absolutely. Einstein, who was a champion of determinism and realism, he firmly believed in an objective reality where properties existed whether we observed them or not. He hated the probabilistic nature. Wolfgang Pauli called Einstein's view the ideal of the detached observer.
And Einstein famously said,
God does not play dice. He just couldn't accept that randomness was fundamental. Bohr, on the other hand, argued that this probabilistic, uncertain nature was fundamental. It was irreducible. That's just how the quantum world is.
So what was one of their most famous philosophical boxing matches? I seem to recall an argument involving a particle going through a slit in a wall.
Yes, that's a classic thought experiment where Einstein tried to find a clever loophole. He proposed, imagine a particle passing through a very narrow slit in a wall. He argued you can precisely measure the wall's recoil, how much it moves back as the particle goes through. From that recoil, using conservation of momentum, you could precisely determine the particle's momentum in the vertical direction. And he said, since you know the slit's position very well, you also know the particle's position as it passed through. So voila, precise position and precise momentum, seemingly bypassing the uncertainty.
Sounds clever. But Bohr
came back with a brilliant counter-argument. He pointed out that the wall itself is a quantum mechanical object. To precisely measure the wall's recoil momentum, you must know its momentum very precisely before the particle even passes through.
The uncertainty applies to the wall, too.
Exactly. By the very same uncertainty principle, if you know the wall's initial momentum precisely, then its initial position must be inherently uncertain. And if the wall's position is uncertain, then the slit's position is uncertain.
So you lose the position measurement.
Precisely. You might gain precision in the particle's momentum through the recoil measurement, but you lose the precision in its position because the slit itself is fuzzy. The uncertainty relation holds. Quantum rules apply universally, even to our measuring devices.
Amazing. And what about the famous EPR paradox? That sounds like another really sophisticated attempt to outsmart the principle.
It was. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, the EPR trio, put forward another very clever thought experiment. This one involved entangled particles.
Entanglement. Spooky action at a distance.
That was Einstein's term for it, yeah. Entangled particles are linked in such a weird way that measuring a property of one particle instantly influences the corresponding property of the other, no matter how far apart they are. So, EPR argued, create an entangled pair, let them fly apart, measure the position of particle A, and simultaneously measure the momentum of particle B. Because they're entangled, measuring A's position tells you something about B's position, and measuring B's momentum tells you something about A's momentum.
So you could deduce both position and momentum for, say, particle A with high precision, even though you only directly measured its position.
That was their argument, yes. It seemed like you could get around the principle for one of the particles without directly disturbing both its position and momentum. They used this to argue quantum mechanics must be incomplete, that there must be some underlying hidden variables determining these properties beforehand.
But that didn't hold up, did it?
No, it took decades, but the physicist John Stuart Bell developed a theorem, Bell's theorem, in the 1960s. He showed mathematically that if these local hidden variables, this deeper predetermined reality Einstein envisioned actually existed, then certain correlations in experiments involving entangled particles would have to obey specific limits called Bell inequalities. But quantum mechanics predicted violations of these inequalities. And crucially, numerous experiments since the 1970s and 80s, most famously by Alain Aspect and others, have overwhelmingly confirmed the predictions of quantum mechanics and violated Bell's inequalities.
So experiments killed the hidden variables idea.
Essentially, yes. They strongly suggest that the weirdness, the uncertainty, and the entanglement are real features of our universe, not just signs of an incomplete theory. The uncertainty principle stands firm.
So, okay, if experiments have basically shut down these escape routes, what does this deep fuzziness actually mean for how we perceive fundamental reality? You briefly mentioned philosophers like Karl Popper and even connections to things like free will or the second law of thermodynamics. This seems to go way beyond just physics formulas.
It absolutely opens up profound philosophical avenues, and people still debate these implications intensely. Karl Popper, for instance, he took a different view. He argued that these uncertainty relations maybe apply more to ensembles, like large collections of particles, rather than necessarily dictating absolute limits for a single individual particle. He saw them more as statistical scatter relations.
So statistical, not absolute for one particle.
That was his interpretation, though it's not the standard view. More broadly, the inherent probabilistic nature of quantum mechanics, which is fundamentally tied to the uncertainty principle, really forces us to grapple with determinism versus genuine randomness. If the universe isn't perfectly predictable, even in principle, at its lowest level, well, where does that leave concepts like fate, or destiny, or even free will? Could quantum randomness play a role? It's highly speculative, but people explore these connections.
And the second law of thermodynamics. How does uncertainty connect to, like, entropy and disorder?
That's another fascinating angle. The second law basically says disorder, or entropy, always tends to increase in a closed system. There are some theoretical arguments that suggest if you could violate the uncertainty principle, if you could somehow know everything about a system with perfect precision simultaneously.
Like Maxwell's demon, but for quantum stuff.
Kind of, yeah. You could potentially use that perfect knowledge to manipulate the system in ways that decrease entropy locally, creating order out of disorder, which would effectively break the second law. So the fact that we can't violate the uncertainty principle seems necessary to uphold the second law of thermodynamics. It suggests these fundamental limits aren't isolated rules, but are part of a larger, deeply consistent framework that governs how the universe works, from the tiniest scales up to macroscopic laws like thermodynamics. It points to a real underlying consistency in nature's rules.
So bringing it back down to earth a bit, this isn't just abstract theory confined to labs and philosophical debates, is it? It has real-world relevance beyond just the historical arguments between giants like Einstein and Bohr.
Oh, not at all. The uncertainty principle is absolutely a bedrock principle of quantum mechanics, and its effects are observed, accounted for, and even utilized routinely in modern technology and science. For example, in spectroscopy, that's the study of how light interacts with matter, how we analyze chemical compositions or the light from stars.
Mhm.
The relationship between an excited atomic or molecular state's energy line width, that fuzziness in its energy and its lifetime, is a direct everyday application of the energy-time uncertainty principle. It's fundamental to how we understand the precise colors or frequencies that atoms emit and absorb.
Okay, so it affects light measurements.
Definitely. And in particle physics, understanding that inherent energy spread, that AE of unstable particles, is absolutely crucial for interpreting experimental results from particle colliders and for discovering new particles. You have to account for that natural width. It's also vital for pushing the limits of extremely low noise technologies. For instance, think about the incredible precision instruments used in gravitational wave detectors like LIGO and Virgo.
Detecting those tiny ripples in space-time.
Exactly. The uncertainty principle actually sets fundamental limits on how precisely they can measure the tiny movements of their mirrors. You run into quantum limits, you can't simultaneously know the exact position and momentum of the mirrors perfectly. This creates what's called quantum noise, a fundamental barrier that engineers have to cleverly design around.
So you can't ever build a perfectly quiet sensor.
Not according to quantum mechanics, no. There's always a minimum level of quantum-induced uncertainty you have to deal with. It shows how this principle isn't just a curiosity, it shapes the very limits of what we can measure and achieve, even with our most advanced technology. It truly reshapes how we view the fundamental building blocks of our universe.
That was a really deep dive into the uncertainty principle. A truly mind-bending concept that tells us there are fundamental limits to how much we can simultaneously know about the quantum world. And it's not a flaw in our tools, but apparently a feature of reality itself. Thanks for listening. Write us your opinion on this. Does the universe possess an inherent fuzziness, this fundamental uncertainty, or do you think there might be a deeper level of reality waiting to be discovered, one that lies beyond the reach of these quantum limits? Let us know in the comments, subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.